String theory is a fascinating framework in physics. It aims to explain the universe's fundamental nature. Unlike traditional theories, it suggests that particles are not point-like. Instead, they are tiny vibrating strings. These strings can be open or closed. They move and vibrate in different ways. The way they vibrate determines the type of particle they form. This concept is revolutionary. It changes how we think about the building blocks of the universe. Moreover, string theory tries to unify all of physics. It brings together gravity and quantum mechanics. This unification has been a long-standing goal for physicists. Understanding string theory can be challenging, but it's a crucial step in understanding the universe's true nature. The roots of string theory trace back to the late 1960s. Physicists were trying to understand the strong nuclear force. This force holds atomic nuclei together. At that time, they discovered quarks. Quarks are the building blocks of protons and neutrons. However, something was still missing. Physicists couldn't explain certain observations. In 1968, Gabriele Veneziano made a significant breakthrough. He found a mathematical model that seemed to work. This model laid the foundation for string theory. In the 1970s, Leonard Susskind and others expanded on this idea. They proposed that particles were actually tiny strings. This was a radical shift from the traditional view. Over the next few decades, string theory evolved. It became a leading candidate for a unified theory of everything. The core idea of string theory is simple yet profound. Imagine particles not as dots but as tiny strings. These strings are incredibly small. They are about 10 to the power of -35 meters in length. That's much smaller than an atom. These strings can vibrate in different ways. Each vibration represents a different particle. For example, one vibration might be an electron. Another vibration might be a photon. This explains the diversity of particles in the universe. Furthermore, strings can be open or closed. An open string has two ends. A closed string forms a loop. These different shapes lead to different properties. For instance, closed strings are often associated with gravity. This is a key aspect of how string theory unifies forces. One of the most exciting aspects of string theory is unification. This theory has the potential to revolutionize our understanding of the universe. In physics, there are four fundamental forces. These are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces plays a crucial role in the interactions that govern the behavior of matter and energy. Traditionally, these forces are described by different theories. This separation has long been a challenge for physicists. String theory aims to bring all these forces together. It proposes that at the most fundamental level, everything is made up of tiny, vibrating strings. It suggests that all forces arise from the vibrations of strings. These strings can vibrate at different frequencies, giving rise to different particles and forces. This is a big deal. The unification of forces could lead to groundbreaking advancements in our understanding of the cosmos. It means that we might have a single framework for understanding everything. This unified theory could simplify the complex equations that currently describe the universe. This concept is known as the theory of everything. It represents the ultimate goal of theoretical physics. For example, gravity is usually described by general relativity. This theory explains how massive objects warp space and time. Quantum mechanics describes the other three forces. It deals with the behavior of particles at the smallest scales. String theory bridges the gap between these two. It offers a way to reconcile the differences between general relativity and quantum mechanics. It provides a way to describe gravity in a quantum framework. This could lead to new insights into the nature of black holes and the early universe. This is a huge step forward in theoretical physics. The potential discoveries and advancements that could come from this unification are truly exciting. Section 5. Types of strings and their vibrations. In string theory, not all strings are the same. There are different types of strings. The two main types are open strings and closed strings. Open strings have two endpoints. Closed strings form a loop. Each type of string can vibrate in different ways. These vibrations determine the string's properties. For example, an open string might represent a photon. A closed string might represent a graviton. The graviton is a hypothetical particle that mediates gravity. The way strings vibrate can get very complex. They can vibrate in multiple dimensions. This complexity allows for a wide range of particles. It's like a musical instrument. Different vibrations produce different notes, in this case different particles. Section 6. Dimensions involved in string theory. Another mind-bending aspect of string theory is dimensions. We live in a three-dimensional world. We can move up, down, left, right, and forward, backward. However, string theory suggests there are more dimensions. In fact, it proposes up to 11 dimensions. These extra dimensions are compactified. This means they are curled up so small that we don't notice them. They exist at every point in our three-dimensional space. These extra dimensions are crucial for string theory. They allow strings to vibrate in more ways. This leads to the variety of particles we observe. Understanding these dimensions is challenging, but it's essential for grasping the full picture of string theory. Section 7. Comparison with quantum mechanics and general relativity. String theory is often compared to other major theories in physics. The two main ones are quantum mechanics and general relativity, which have been foundational in our understanding of the universe. Quantum mechanics describes the behavior of particles at a very small scale, such as atoms and subatomic particles. General relativity, on the other hand, describes gravity at a large scale, such as planets, stars, and galaxies. These two theories work exceptionally well in their respective domains, providing accurate predictions and explanations. However, they don't work well together when we try to combine them into a single framework. This is where string theory comes in, offering a potential solution to this problem. It aims to unify these two frameworks into a single cohesive theory. String theory provides a quantum description of gravity, which is a significant step forward. For example, while quantum mechanics uses point particles, string theory uses one-dimensional strings. This fundamentally changes how we think about particle interactions and forces. Similarly, general relativity uses a smooth fabric of spacetime to describe gravity. String theory adds extra dimensions to this fabric, which could help explain various phenomena. This unification is one of the most exciting prospects in modern physics, potentially leading to groundbreaking discoveries. Section 8. Practical implications of string theory. String theory is a theoretical framework that attempts to reconcile quantum mechanics and general relativity. While it may seem abstract, it has practical implications that extend beyond theoretical physics. It fundamentally changes how we think about the universe and its underlying principles. This new perspective can inform other areas of science and technology, leading to groundbreaking innovations. For example, string theory can significantly influence how we understand black holes. Black holes are regions of space with intense gravity, where traditional physics breaks down. String theory suggests new ways to describe these enigmatic regions, offering insights that could lead to new discoveries. It can also impact our understanding of the Big Bang, the event that started the universe. The Big Bang is a cornerstone of cosmology, and string theory provides a framework for studying this monumental event. By offering a new lens through which to view the Big Bang, string theory can help us unravel the mysteries of the universe's origins. Moreover, string theory can influence material science by providing insights into the fundamental nature of particles. Understanding these particles at a deeper level can lead to the development of new materials with extraordinary properties. These materials can have unique properties, such as being stronger, lighter, or more conductive than anything we currently have. The potential applications of these materials are vast, impacting technology and industry in profound ways. From advanced electronics to aerospace engineering, the implications of string theory are far-reaching, promising a future where science and technology are deeply intertwined. Section 9. Potential applications of string theory. Beyond theory, string theory has potential applications. One area is in particle physics. It can guide experiments at particle accelerators. These are machines that smash particles together. They can reveal new particles and forces. String theory can also impact cosmology. Cosmology is the study of the universe's origin and evolution. It provides a framework for understanding dark matter and dark energy. These are mysterious substances that make up most of the universe. Moreover, string theory can influence quantum computing. Quantum computers use the principles of quantum mechanics. They can perform certain calculations much faster than classical computers. Understanding the fundamental nature of particles can advance this technology. Section 10. Current status of string theory. String theory is still a work in progress. It's a leading candidate for a unified theory, but it has not been proven experimentally. This is a challenge for physicists. They are working on ways to test string theory's predictions. One approach is to study high-energy particle collisions. These collisions can reveal new particles predicted by string theory. Another approach is to study the early universe. String theory makes predictions about the Big Bang and cosmic inflation. Despite these challenges, string theory has made significant progress. It has provided new insights into fundamental physics. It has also inspired new mathematical tools. These tools are useful in other areas of science. Section 11. Future prospects of string theory. The future of string theory is full of possibilities. Physicists are optimistic. They believe it can be a key to unlocking the universe's mysteries. One future direction is to find experimental evidence. This is crucial for validating the theory. Another direction is to explore the theory's implications. String theory can influence many areas of science. This includes particle physics, cosmology, and technology. It can lead to new discoveries and innovations. Moreover, string theory can inspire new theories. It can provide a foundation for future breakthroughs. As our understanding of the universe grows, string theory will continue to evolve. It will remain a central topic in theoretical physics.